Hi everyone, thanks for joining me on Last Minute Maths. And this one is going to be a question on Cambridge STEP paper from 2014. And it's question 7 from the Step 1 paper. Now, before we jump into the question itself, thank you so much to Vinicius for requesting this question, and also to Tom and other viewers who have offered their comments, suggestions, and even questions. So thank you all very much for your support. All right, let's go into the question itself. All right, it's based on vector geometry and based on a triangle, etc. We'll go through it one by one. But just to say, I'll go through it assuming obviously vectors knowledge, but also some of the further maths material that you might have covered if you're considering Cambridge STEP. All right. If anything is confusing, then obviously leave your questions in the comments and feel free to forward through the video, rewind, pause, etc., or even watch it at double speed if you just want to see the solution. All right. Hope it helps. Right. So what's this question all about? It's got a triangle, and I'm going to just refer to this diagram here below. So you've got a triangle OAB, right, as you can see, and it starts giving you some data, all right? So D, the point D here, divides side BO. Now watch out, they've referred to the direction as being BO, not OB like we would normally assume, in the ratio of R to 1, so that BD is R and DO is 1, all right? And the point E, right, there, divides side OA in that direction in the ratio S to 1, all right, where R and S are both positive, okay, so nothing negative in those. So the question is actually asking the lines AD, all right, so it's effectively doing that, and BE, there, sorry, bit bent, intersect at a point G, all right? And they want us to show the position of G as being this rather nasty looking algebraic expression in terms of A and B, where OA, right, is A, and B is your position vector relative to O, all right? So that is basically B, etc. Okay, and G is that, the position vector. Right, so we're going to start now, the actual solution. Very basic system in terms of writing down what we do know already. So OB is B, OA is A, and BD is R times DO. All right, OE is S times EA. So that's all in the question, just recapping so you have it in front of you. Okay, so now we're going to actually write down some vector quantities. So from this, we can see that dB is actually R over R plus 1, all right? So R is the dB bit, and R plus 1 is the OB bit, all right? So that simplifies simply to R over R plus 1 times the vector B, all right? When I'm using the small letters, I'm not going to do any sort of like underscript, overscript, or whatever. Just A and B are vectors, okay? So OD, therefore, must be 1 over R plus 1 times B, all right? So I'm just writing down the obvious vectors just so that you can see exactly what's going on. OE, in exactly the same fashion, is S over S plus 1 times OA. So that gives us that result. And similarly, EA is 1 over S plus 1 times A, all right? So we have all the basic components that we need. Note from your A-level and perhaps further maths vector geometry and vector line equations that lines can be defined by a point and a direction. All right, and that's all you need really to define a line. So the parametric form of lines, which many of you will call the vector form of a line, can define any point on that line. All right, so this is the general form that you're probably used to seeing. R being a position or a point or position, and you're starting with a particular point P, and Q is a direction, and lambda is some proportion, whether it's fractional or integer or greater than 1, whatever it may be. That's just some multiple, and it's scalar. All right, I better write that in as well. There we go. And lambda is obviously a real value. Okay, so using what we've just talked about, the line through A and D is R1 equals OA. So we're going to A and then some proportion of AD. All right. That doesn't really need much explanation. I'll leave it as that. All right. So putting in the vector quantities, A is the position vector of A, lambda times OD minus OA. Remember, we're going from A to D, and I'm going to just quickly jump back to the diagram. From A to D, we're going to go A to O, which is minus A, and then we're going to go to OD. All right. So coming back to this, AD equals AO plus OD, and that is effectively minus A plus some component of the line B. All right. So shall we call it lambda B if you like for that part? But let's just say B for the moment, something like that. Excuse me. When we actually work out the details of that, so we have A, OD from what we did at the beginning of the question, 1 over R plus 1 times B minus A, the whole thing times lambda. All right. So this bit here is the OD component. All right. Some multiple of B and minus A. So expanding the brackets, tidying it up, we have A minus lambda A. So that's 1 minus lambda times A. And then lambda over R plus 1B. All right. So that is the position along AD. All right. Let's call that R1. Then in very similar fashion, exactly the same methodology, the line through B and E. All right. Going from B to E. So that's OB. So we're going to go from O to B and then some element B to E. All right. So OB is your starting position again. All right. Note that. So you have mu times OE minus OB. All right. Remember the original diagram again. I'll rewind to it 1 second. So we need effectively minus B and then along to go to E. All right. So that gives you a BE element. Okay. So coming back down here again. Oops. There we are. Right. So again, inserting the bits that we do know and expanding everything out, it's exactly the same format. We get 1 minus mu times B and mu s over s plus 1a. All right. If you need to pause here and just verify that for yourself, then please do so. All right. Okay, so the intersection of lines is when R1 equals R2, all right? So the coefficients of A and B must be equal, all right? And that's just a basic concept. When two lines intersect, their position vectors must be equal. So if we are equating the coefficients, then from the two equations we have above, we have looking at A, the component A, then mu s over s plus 1 must equal 1 minus lambda. All right. Just again to verify that, here's your mu s over s plus 1 for A. And in this one, you've got 1 minus lambda A. So those two must equal each other. Multiply across denominator, all right, basic algebra. Mu s equals s plus 1 minus lambda times s plus 1. Again, tidy it all up, and I have an equation with lambda and mu with coefficients equals s plus 1. All right. Same process for B. And again, going back, in the second equation, B is 1 minus mu is the coefficient. And the other one is lambda over r plus 1. All right. And there we go. And so, again, multiplying by r plus 1, you've got r plus 1 minus mu times r plus 1 equals lambda. Bring it round, tidy it up, and you end up with lambda plus mu times r plus 1 equals r plus 1. So effectively, we have two simultaneous equations in variables lambda and mu. Now, I'm going to jump to a slightly different method to solve this, which I think is much more elegant than normal going through, let's say, simultaneous equations of eliminating variables and so on. If you were to start eliminating variables, you'd have to multiply, for example, the first equation by s plus 1, all right, and subtract 1, from the other, etc. And it gets a little messy. You're going to start getting sort of like long-winded algebra, but it can be done. So you could use the elimination method. There we go. However, what I've chosen to do is to use the matrix method of solving an equation system. And I don't know, it might help. It's just another way of looking at it. Those of you who have studied matrices, and you probably should have done by the time you're considering step questions. And so this, I think, lends itself to a slightly better solution or simpler solution. So we take the coefficients, as you can see, 1, and here we have the coefficient of mu. Down here we've got the coefficient of lambda and the coefficient of mu again in the second. All right. So that's where we get the matrix M from. I've labeled that as M. All right. And the matrix is 1, reading across R plus 1, bottom line S plus 1, S. So 2 by 2 matrix. All right. Times the variables lambda and mu. And the results are R plus 1, S plus 1. All right. So what we need to do in order to solve this, because effectively we have M times lambda mu equals, let's just pick any random number, I know, mn if you like. And so in order to solve it, lambda mu will be the inverse of m times mn. All right. Okay, so that's what we're trying to do. We want to find the inverse of the matrix M. The first step in finding a matrix inverse is to find the determinant, right? And for a determinant, a little bit of revision, right? You're going to have AD minus BC, okay? So that's exactly what we have here. S times 1, right? So that's A, B, and C, D. Whoops. there. Please don't confuse this with the vectors we have above. This is just to show the matrix formulation. So once we expand those brackets out, tidy it all up, you end up with minus brackets r plus rs plus 1. The reason I've left the minus out deliberately, I reversed it out, is because this matches the denominator in the question, which I think the way they had it, they had 1 plus r plus rs, I think. All right. So it straight away brings us sort of in the right direction as far as the question is concerned. And then the actual inverse matrix is 1 over the determinant. So it's 1 over the determinant times the transpose of the matrix M. So what we do, we change the matrix format around. There. That's the transpose, just in case you need a reminder of that. All right. So this is my inverse matrix. If I now multiply both sides, I suppose, with the inverse matrix, I get the identity matrix on the left-hand side, and I will get lambda mu equals inverse of M times the original two solutions. So I'm going to actually work through that. All right. So this bit is my inverse of M, and you can see the transpose of M. All right. And let's actually multiply through. What I've done is I've taken the minus out. All right. I've multiplied everything in the matrix by the minus, so just getting rid of that nice and early. Then when we multiply the elements of 2 by 2 by the column matrix here, so you got the components here, s plus 1 times r plus 1, all right, and you've got minus s times r plus 1, all right. Bottom component, the bottom row, s plus 1 times r plus 1 again, minus brackets s plus 1, all right. That should be fairly evident. Again, pause and work through it if you feel you need to, all right. Okay, so after all of that, we get a solution for lambda and mu, all right. So lambda equals the top row of that, and the bottom row is mu, all right. So what I'm going to do is use the lambda value from this matrix. So lambda equals, as you can see, r plus 1 over r plus rs plus 1, all right. So remember again the original equation that I had for r1, all right. I'm going to just substitute for lambda in both those cases, all right. So that's your lambda there, and this part, how should I write this there, is lambda, all right. So when you again tidy all that up, remember that that cancels with that, and you end up with the position r, right, that we're looking for in this case, is given by rs over r plus rs plus 1, all times a, plus 1 over r plus rs plus 1, all times b. That, the intersection of the 2 points, is g. So that is as shown. That's exactly what they were after in the question, all right? And you could always use mu to verify that the solution is valid. All right, so that's the first part done. Not as painful as it might have appeared, but watch out for the matrix method. You're welcome to use the alternative elimination method. All right, okay. Second part of the question. Now, this part of the question actually says, and I'm going to go back to the original question. Let's do that quickly. And it says, the line through G and O, all right, so basically OG, meets AB at F, all right? Given that F divides AB in the ratio T to 1, find an expression for T in terms of R and S. let's get all those words into a diagram. So in the second part of the question, we basically have, as you saw earlier, that. And so that's G. And you've got a line connecting OG, and it's going to hit AB at F. So that's your G there, and that's F. All right. And we're saying that that is a ratio of T to 1. Okay. So I'm going to let the line through O and G be L1 is some multiple alpha times OG. All right. So that's the statement there. So L1, expanding on what we've learned for G, the position vector of G, from the previous part of question, from part 1. And so a multiple alpha times that, okay? And then a line through AB, or A and B, if you like, is starting with your position A, all right, so at A, and then some multiple, if you like, of the line segment. Okay, this is a line segment rather than an infinite line. Line segment AB, all right? And I'm going to just introduce a variable just for my own comfort, is beta is a fraction, because obviously we are going a part way down there, all right? So I'm going to call that beta as a fraction of the whole AB, all right? Again, going back, AB is OB minus OA, all right? And replacing all those with vector terms, we get A plus beta times B minus A, all right? And tidying that up, we've got 1 minus beta times A and beta B, all right? So again, the same thing, all right? We know that the lines must intersect at F. So we set line 1 equals line 2, and we are going to equate the coefficients, all right? Equate coefficients. Again, so 1 minus B, right, for the A components, 1 minus beta, equals alpha times RS over R plus RS plus 1, which is from the original equation we were given, all right? And similarly, for the B component, beta equals alpha times 1 over RS plus 1. So both of these are from the, let's say, equation for G, all right? So eliminating beta between these. So I've got beta expression there. I'm just going to put it straight into there, all right? And replace that, eliminate beta between the two. So what I end up with is 1 minus alpha over R plus RS plus 1 equals alpha times RS over R plus RS plus 1, as you can see, all right? So a little bit of algebra. I'm not going to bore you to death with rearranging bits and bobs and whatever. But as you can see, if I take all of this to the other side, etc., I can then rearrange, factorize alpha out, and I have alpha times 1 plus RS over R plus RS plus 1 equals 1. All right. So rearranging alpha, I have a solution for. And once I know what alpha is, if I put it back into, remember that one there, then I know what beta is. And this is what I was looking for ultimately. All right. So that's actually my solution in terms of what the beta fraction is. Finally, to polish off the question, remember that's your A, B line segment. All right. This is fraction beta, and this must be 1 minus beta. Okay. So for example, if this was 1/3, then that must be 2/3, etc. All right. That's not what it actually is. It's just a representation. And we know that the question said that AB is split by F in ratio of A to F is T to F to B is 1. All right. So therefore, from this, T over beta must equal 1 over 1 minus beta. Tidy it up. You get that one there. And remember that beta was 1 over 1 plus RS. All right. Substitute that in, and you get, well, what you can see, rather than reading all that out. Okay. And multiply top and bottom by 1 plus RS. Okay. And you end up with the expression there, which, as you can see, the whole thing simplifies to T equals 1 over RS. All right. So that is the whole question, and I hope it's made sense to you. And if you still have any questions or any area that you want clarified, or even the matrix method for solving equations, then please do drop it in the comments. Any questions, any suggestions, as always, much appreciated. And if you found it useful, then please do share it with others and subscribe and help support my channel. All right. Thank you for watching.